Welcome to polynomial functions.
Before we begin our study of polynomials, let's look at the polynomial definition. A polynomial is a sum of terms that satisfies the following expression. We have a sub n times x to the n plus a sub n minus 1 times x to the n minus 1 plus, notice here that we have these three dots. That just means that we continue with this pattern inside here with maybe one or more terms. And then we have plus a sub 1 times x plus a sub 0, where the AI's are real numbers. So this AN, this AN minus 1, A1, A0, those are all real numbers, where N is a whole number. So whole numbers are going to be numbers such as 0, 1, 2, 3, and then we just continue in this pattern. So whole numbers are just your counting numbers plus 0. So let's look at some key components of our polynomial. Notice here that it says that a polynomial is a sum of terms. Terms are going to be the parts of the polynomial that are separated by a plus sign, or you may see a minus sign as well, but remember, if you see minus, it's just plus negative, whatever the term is. But they're separated by the plus signs here. And then the term with the highest powered exponent, this is called the leading term. And you can see that here. The reason it's called the leading term is because this has a power of n. If you notice, the next term has a power of n minus 1. So let's say that n was 5, then n minus 1 would be 4. And then, you would continue to go further down on your powers of exponents as you get to the end of the polynomial here. A sub 1 times x, we don't see a power written here, but it's understood that this is a 1. And then we have a sub 0. You don't see an x written, but we have an understood x to the 0 here. We just don't ever write it. And the reason that's x to the 0, if you think about it, a to the 0, that's equal to a to the 0 times 1. And anything to the 0 power is equal to 1. So x to the 0 is actually equal to 1. So a sub 0 is equal to a sub 0 times 1 is equal to a sub 0 times x to the 0. And this is what we call our constant term. And what's cool about the leading term here is the leading term is what dictates what happens to the polynomial as it moves towards positive or negative infinity. Since it has that higher power of x, it's telling you what the polynomial is doing at the extremities. Whereas the constant term doesn't do that. But the constant term is important because it actually gives you the y-intercept of the polynomial. And we'll see that a little bit later when you get into graphing polynomials. On our next slide, we're going to be looking at formulas of polynomials versus non-polynomials. What you want to keep in mind when you're looking at those is that n, your power, needs to be a whole number. So it's a number 0, 1, 2, 3, 4, 5, 6, and so on. No fractions, no negative numbers. So our first column here is a polynomial column. Notice that our first polynomial here is 2x to the 5th plus 3x to the 4th minus x. It has those key characteristics of polynomials where we have real numbers as coefficients, 2, 3, and negative 1. And I say negative 1 because this is the same thing here as we do 2x to the 5th plus 3x to the 4th plus negative 1 times x. So if I have minus x, it's the same thing as having a coefficient of negative 1. Also notice that our exponents are whole numbers, 5, 4, and an understood 1 right here. So this fits the definition of polynomial. Let's look at the next one. We have 2x over 3 plus x. Well, that can actually be written as 2/3 x plus 3. So we have our leading term, 2/3 x, and then we have our constant term of 3. Notice that we didn't see a constant term up here. Just know that this is going to be plus 0, so 0 would be our constant term there. For our third one, we have 2x. This is just a single term, but that's okay. A polynomial can have just one term as long as it fits the definition. We have a real coefficient 2, and then we have a power of 1. So this is a polynomial. And then the next one we have is 3, just the constant 3. Remember that 3 equals 3 times 1, which equals 3 times x to the 0, because x to the 0 equals 1. Okay. So this is another way that we can write our polynomial here, but we usually just write it as a single constant like that. And then we have the last one here is 2x plus 3 over 4. That one looks a little bit different, but we can actually rewrite this one as well. We can divide 4 into each of the terms that we have on top. If I take 2x and divide by 4, I'm going to get 1 half x, because 2 over 4 is 1 half, plus 3/4. Notice here that we have fractions, but that's okay. Remember that the coefficients of polynomials can be real numbers, and fractions are real numbers. Now let's look at some non-polynomials. For the first one, we have 2 times x to the 1/2 plus 3x. Can you see what the problem is on here? Notice that we have a power of 1/2. That is not allowed, okay? We cannot have anything but a whole number up here. So this is not a polynomial. Let's look at the next row. Here we have 2 times the square root of x plus 3x. If you remember, the square root of x is equal to x to the 1/2. And in fact, any radical that you have can be written as a fractional exponent. For example, let me just write that rule up here for you. So if I have x to the m over n, that equals the nth root of x to the m. Okay, and for the square root, n is 2, and then the 1 is the power of x that you have there. But anytime that you have a radical, remember it can be written as a fractional exponent, which is not allowed because a fraction is not a whole number. So this one again can be written as 2x to the 1/2 plus 3x. This is not a polynomial. And in fact, any radical function that you have can be written as a fractional exponent. And so no radical function will be a polynomial. Because again, polynomials, you cannot have a fractional exponent. It has to be a whole number. Let's look at the next row. Here we have 2 times x to the negative 1 plus 3x. Are we allowed to have negative exponents? No, negative exponents are not whole numbers. This is not a whole number, which means that this expression here is not a polynomial. Now let's look at the next row. We have 2 over x plus 3x. Well, this can be rewritten as 2 times x to the negative 1, because anytime you have an x in the denominator, you can rewrite it with a negative exponent, and then plus 3x. So notice that we have the same thing that we had on the previous row. This is not a polynomial. We have a negative exponent. It's not a whole number. Now let's look at the last one. Notice here that we have 2x plus 3 over 4x. Notice here again that we have an x in the denominator. You cannot have an x in the denominator. It's okay to have a fraction like we had over here on the left because the x wasn't in the denominator there. But on this one, even if we tried to rewrite it, let's rewrite it. I have 2x over 4x is going to be 1/2. The x's will cancel there, so it's just going to be 1/2. But when I have 3 over 4x, nothing will cancel there. And in fact, you know, if you wanted to explain it even further, this is the same thing as 3/4 times x to the negative 1. So we have a negative exponent there, which you're not allowed to have. Okay? So you don't always have to rewrite it as a negative exponent to see it. If you can just see that if you have an x in the denominator, like these last 2 examples, that is not a polynomial. For example 1, we want to determine whether the functions are polynomials. For part A, we have 3x over 2 plus 4. If you wanted to, you could rewrite it. This is the same thing as 3/2 times x plus 4. Notice that we don't have any issues with having an x in the denominator. We had a 2, but that's okay. We have real coefficients, right? We have a 3/2 and we have a 4 here. And our powers of x are just whole numbers. Here we have a power of 1. If I have a 4 here, that means we have an x to a power of 0. Those are whole numbers. So this is a polynomial. Let's look at the next one. We have x to the negative 2 plus 4x minus 2. Notice that we have this negative 2 here. This is not a whole number. This is not a polynomial. Or we can just say a non-polynomial.